All right, guys. So we're gonna start from question 8 now. So we see that this function, the first one is Ben, Danielle, Chris, and Ben goes to by F to this guy. So you see that this function is this relation F is belongs to A times B. It is a function and is a one-to-one and it's onto as well. So this one is bijection, or by it is a bijective function. So the other one, F, actually Ben, Danielle, and Chris, all of them goes to 1. So 1979. So actually this is not one-to-one, not one-to-one. So because of this, F is not invertible, and as a result, F is not bijective. A function is bijective if it is one-to-one and onto. Okay, a function, which is, we already know that it's a function, and if it is one-to-one and it's onto, so we know that it's bijective. So it's not one-to-one, as a result, it's not bijective. So if you have something like this, so this means it's not a function. So a person cannot have two birthdays. So not a function. It might be one-to-one, it might be onto, but it's not a function. So it's not bijective as well. So it works to consider this one. So if we have something like this, so this Ben can become here, Daniel can go to this one. Okay, anyone. It should be corresponding. So it is a one-to-one onto function. So this will be a bijective. If you have several inputs goes to only one output, as long as there is no two edges from one input to different outputs, then it will be function. Okay, good. Onto, because it covers all of the destination set, but it's not one-to-one because it receives several inputs and it gives us only one output. And this is not function because it's not functioning logically. Okay, so one input gives us sometimes this output, and sometimes it gives us like this output, which is not good. Now, let's do this one. An isomorphism between two graphs is a bijection function between the vertices, provided that it preserves the edge structures. Okay, we will see the meaning of the edge structures. So if AB belongs to EG, then it should be F of A and FB belongs to EH. So it's the corresponding edge should exist here, and the corresponding edge B, it should exist here as well. All right, so G is a different graph, H is a different graph. So let's have a look at this graph here. G is this one with these edges. EH is the edges of the graph H, which is here. All right, so it's here, and we can fill out this one. So if I have WY here, so WY here, then it should be RM definitely. So because if I can stretch this one, and L T R B. So this one is here. And this one is for this one. Okay. So I'm gonna write here RM and WX. So this one here definitely comes for this one. Okay, RB. So it preserves the structures. So, okay, and we can see that this is an isomorphism between these two graphs. All right, just quickly, let's go to the other question. All right, so this question asks us this, one of these graphs are like belonging to one of these um, graphs that which is this described here. So let's draw these graphs. So we see that A, B, C, D. So from here, all right, A to B, A to C, A to D, and yeah, so it's this one. So it will be K1, 3, which is describing this one bipartite graph with this one. Now about this B, so we see that A goes to B and A to C, A to D, and from B to A, B to C, B to D, and from C to, and from C this one to A, which is existing already, C to B and C to D. So this one here. So it's a complete graph. So it will be K4, which is part A. And this one is the interesting one, is A goes to B. All right, A goes to C. Okay. And B to A, B to D. Okay, so the other one is C to A, yes, C to D, and about the D, D to B, D to C. So can I flip this one? A, C, B. So I want to write this one like this. D is here. So definitely this is this one, which is like, okay, so 1, 1, and here is 1, 0, definitely. So which is like together, they are isomorphism. All right, so now let's do question 11. Okay, an invariant of isomorphism of a graph is a property that which does not change under the isomorphism. All right, so list of all invariants for isomorphism between graphs that you think that they will exist still, they will be preserved. So I can say like number of the vertices firstly, number of the edges, this is part A, definitely. And so if we have the same edges and the structure preserved, so number of the degrees, and So yeah, so the other things like such as faces, I don't know, faces, paths, in terms of like it has cycle, Eulerian cycle or Hamiltonian cycles and other things. Yeah, so the important one are these ones. Okay. Now, two of the following graphs are isomorphic to each other, and the third one is not isomorphic to either to the other ones, which for the isomorphic graphs prove the isomorphism. For the non-isomorphism graph, show that it is not isomorphic. The other two. Now, here we see that G obviously is not isomorphic with H and is not isomorphic with F. Okay. So one of the reason, obviously, because of this. So this has like 3 degree. This has 3 degree. This one, 1, 2, 3. All right. So this one has 1, 2, 3, 2, 3. Yeah. So several degrees, 3, 3, 3, 3. So but all of this one is like 3. Here is this one. So for F, now I wanna define the isomorphism like this one. F of VF goes to F of VH, and F of, I have got A, B, C, D, E, F. So it is equal to, so A1 is this one. So M is this one. So from here, I should change the color. Yeah. It goes to E, goes to C, and it goes to B. So I will have, this one is like, it goes to N. Okay. So I would write M. So N. Okay. So if this one goes to R and P. So I can write P. So this goes to C1. So I write C. Okay. Then after, sorry, this P. And from here also D. There is a D here. So D is not connected to, so D is not connected to this one. So I should, okay. All right. So D is not connected with A, so I need to choose some vertex that which is not connected to M, so I can't choose Q, just wanna preserve the order. So from P, I was here, C, so it should go to the D. So P to R, which I have not chosen yet. So it will be P, R. Okay, am I right? And so I have come here A, B, so A, B, C, D, E, F. So E comes here. So I'm here, R, and I can go here or go here. So I have chosen this one already. I have chosen this, I have chosen this one already. So this one is the one that I have not written yet. So I will write this one. after Q, and so F, this is from E to F. F is the one that corresponds connecting to B and D. So I will choose, so let's write here as well, A, B, C, D, E, F. So I will choose something like this now. Here, E is here, E is here, so it goes to the F. So Q, it was here, and I will choose O, so I have just one option, definitely. So O, I was just confused. But I wanna just analyze the proficiency. So from here, O, this one, it has with D and B. So O should have with N here, O with F with B. So O must have a connection with N. So O should have a connection with. So this is not right. So I need to, guys, this is like a little bit confusing. Okay, so here is the one that I wanna choose work again. So M comes here, okay. So A comes here, all right. B should go to the F, so B should go to the C. M instead of P, I prefer to go to the R this time. So I will go here, R. So I'm writing C here. So I will choose D1, D. So D goes here. So this time D goes to here. I decided to be this one because D shouldn't have a connection with A, and R, if I chose Q, it should have a connection with the M, this one here. So I chose this one. So I will choose P, not Q. And now between after P, I should have R. I have chosen R already. Okay. I should choose now O. And now I wanna choose after O, what do we have? Q. Okay, so this one is E, this one is F. Okay, can I sanity check? Okay, so E connects to the D and F. So O should connect to the D, which is here, and O should have a connection with Q. That's right. So that's right, of course. And what else do I have? Can I check O? So O should have a connection with E. Each have a connection with D and F. So O should have a connection with Q, this one with Q, and should have a connection with P. Yes, that's right. So that's now right. Okay. That's all. So this is really now right. So like we can see that. So we can write something like this. So I don't want to rewrite again. Okay, so we can draw something like this table here. Okay, so where's that? It's here. So you can say like E, A, what was it? Okay, let's write like this. EAB corresponds with EMN. The edge between vertex M and N. Okay. And you can continue like this one. All right, so it will be something like this table here. So you can continue for sure. Okay, now let's do this one. A planar graph can be drawn in the plane with no edge crossing each other. Okay, so we shouldn't cut any edge. So we don't have a breach. A common way to draw K4 is a square with parallel crossing the diagonals like a square. But can K4 be drawn without edge crossing? Yes, the famous one is this one. Okay. So it didn't work. So let me do it again. Okay. Okay, so this one. Yeah, that's right now. That's right, for sure. Okay, this one. So this one or this one. Okay. So K4 is planar now. Okay, so you can rely on this. So the idea is this. So you wouldn't do this one. So you shouldn't cross the diagonal. All right. Let's go to the other question now. When a planar graph is drawn with no edge crossing, its edge divided the plane into regions called faces. The area outside the graph is also a face. Okay, so K3 is a graph, planar graph. How many faces does it have? So can I have this one? K3 is like this guy. So 1, 2. So just two faces it has. Euler formula, which tells us that if G is a connected planar graph with V vertices, E edges, and F faces, then we've got this formula. This is, guys, this is right in the polygons as well. All right. So if you have this one like this, okay, you got 6 faces minus, should use this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you got 12 edges plus 8 vertices. So 14 minus 12 will be 2, which is right. So this Euler formula that is right for the polygons as well. So now K3 is this one. So what is the difference of this question? Yeah, so K3 is the like verifying the Euler formula. Actually, we did it for this one, the fancier one. So here we've got 2 faces minus 3 edges and plus 3 vertices. All right, so 5 minus 3 is 2, which is right. Now this one is like this polygon, sorry, the graph is also okay. So outside 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So am I right? Actually. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. Okay. So 5 here, 6 here, 7 here. 8, 9, 10, 11, 12. So yeah, 12 faces. All right. And minus how many edges? Oh, okay, it's a lot. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay. So did I miss 27? 28, 29, 30. So I hope it is right. That's right. I hope it is right. And vertices. Oh my God. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20. Okay. Oh, that's right. So, okay. So I was not sure about this 30. So, but it's right. If you have the polygon, the three-dimension version, so I don't remember the name of this one, but so I don't remember the geometric version of this this guy. So actually, in case if there is a question that why do we count the face outside of the outside region is as a one face, the geometric version, you see that you can assume that you got this one, there is like a base that you don't see under this one. So that is one face. So, but in the graph, you can count the outside. So it will be another face. All right. Let's do question 16. Okay. Now, let's assume G is a planar graph. For each face in G, define a vertex in a new graph, which we call it G star. And for each edge between those graphs, each edge between those two faces in G, let's define one edge connecting the corresponding two vertices in G star, actually connecting two faces in G. So G star is a planar graph for sure, and it is called the dual graph of G. So K3, let's assume that we've got the K3 here. Okay. One face here and one face here. So I will add one vertex, this one. And because of, so let me count, actually this not good idea. Face, one face. So because of this edge, I have this edge. So because of actually how to say this edge between these two faces, I have one edge here This face means this vertex, this face means this vertex. Now, because of this one, we will have another one. And because of this edge between those two faces, I mean here and here, so I will have this one. So the answer of this one will be something like, oh my God. So this one and this one. Okay. Now, question 17. The graph below is a graph of an octahedron in three-dimensional space. An octahedron is a solid. So I was like, I was searching for this actually. So 1, 2, 3, 4. So 4 faces there and 4 faces down. So octahedron. So I was actually searching for the one like with the 12 faces. I don't remember the name. Okay, so there are a lot of them. So this is this guy. Okay. Okay, so what we wanna do, the face outside. Okay, we wanna so we need to let's firstly draw the planar version of this one. So this guy. Okay. Actually, it is hard. Okay. So there should be something here as well. Here. There's some here. And I need to check this one. Okay. So I couldn't this one. I couldn't do this one. Let me rethink about that one again. So this will be like this one. If I don't make a mistake. Okay, let's. This one comes here. Six. Okay, it will be like this one. So I need to analyze. So there is this one as well. Okay, so if this face is like for this one. Okay, so we got this one here. So it is this one for this one. And yeah. Yeah, we are right now. But we can talk about this one later as well again. But anyway, so I wanna do this one. So I can use this one and inside this one. Okay. So the face will be this one, and this one. Okay, so let's do from here. So here. This one. Yeah. For this one and for this one, I draw it here. So this one has a face with this. So this one and with this one. Okay. And there should be something here as well, which is with this one and with this one. Okay. Now for this one, there should be something here. So can I draw it here? So it should be with this one. So it comes here. And there should be something here as well. So I will draw it this one. So this has this one. So like this one. And this one has with this one. So it is this one. And there should be something here as well. There should be this one with this one. Okay. So yeah, it's a little bit irregular, but definitely this is Q3. Okay, I just followed this rule, this one and this one. Okay. For drawing this one with this one, you can do it for sure. So you need just to think that without drawing this one, it is possible to draw this one with this one, which I tried already, and it is possible. Okay. So now about this question, last question, we see that can you find two different planar drawings such that are not yeah, so let's do this one. Okay, this one, this. So what is the dual graph? Okay, so the dual graph here is here. Can I try with this? Okay, so here this face, here, this face, here, this so from with this edge as well, with this edge as well. So this one and this one. There is another one here. Okay, let's call. And this one with this one. And with this one as well. There is this face as well here, and it has with this face, yeah, and it has with this face as well outside. So can I do with this? There should be this face as well, twice. Okay, and this has with this face as well, which is this one. All right, so let's sanity check. I started with this, which is here. So 1, 1, 2 is this one. Okay. Then 3 here. Then 4 here. So 4 has 2, like for this one is like another edge between 1 and 4. All right. Okay, so number 5 is this one. Okay, so it is like 5 twice with 1, so 5, so twice, and 5 one time with 4. Okay, 4 does only 1 with 3, 3 only with 2, so that's right. Now the corresponding of this guy, so this guy is corresponding with this one, so it is this one. Okay, so can I do this one? No. 1, it is here. 2 here. This guy is also 3, so it has with 3, and it has with 2 as well. So how many with 2? Just one time. Okay, so let's call this one 4. So 4 has with this one, 3 with this one. Does it have with 1? No. So let's call this one 5. 5. Also, let's call this one 5 here. 5. So 5 has not got to do with 3. 3, of course. So let's not do that there. 5 here. And 5 twice by 1. Okay. So let's see why it's not like isomorphism with this one. So I can see that 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And 1, 2, 3, 4. So I don't have any vertex which can have like 6 degrees. So it is 6 degrees 6, and this one is degree, doesn't have a degree 6. So the other one is like, we can count. Let's count 1, 2, 1 edge, second edge, 3, 4, 5, 6, 7, 8 edges. So how about this one? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's count it again. 1, 2, that's right. 2, 3, 4, 5, 6, okay, 7, 8. So this one is let's count it again. So I just made a mistake. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this one has got 9 edges, but this one has just 8 edges. So they are not isomorphic. Okay,